Hello there, and welcome to the Sleepy Science Society. Tonight, we are drifting into the quiet world of winter's most delicate creation, the snowflake. These tiny, crystalline sculptures appear so simple at first glance, yet they hold within them mysteries that have captivated scientists for centuries. Each one is a frozen moment of atmospheric storytelling, a miniature work of art shaped by invisible forces dancing through the clouds. As you settle in for this gentle exploration, imagine yourself standing outside on a winter evening. The air is cold and still. Fat snowflakes drift down from the dark sky above, each one catching whatever light exists, each one different from all the others that have fallen before or will fall after. If you've ever caught a snowflake on your mitten and looked closely before it melted away, you've witnessed something extraordinary. You've seen a structure that no one else in all of human history has ever seen in quite that form. And no one ever will again. If you enjoy these peaceful journeys into science, I invite you to like this video, subscribe to the channel, or share your thoughts in the comments below. It helps other curious minds find their way here, one sleepy soul at a time. But for now, all you need to do is rest. Let your shoulders drop. Allow your breathing to slow. Let your mind drift gently into wonder as we explore the science of snowflakes together. The snowflake sitting on your sleeve for those few precious seconds before it vanishes is not just frozen water. It is a chronicle written in ice, a physical record of every moment of its journey through the atmosphere. The temperature zones it passed through, the humidity levels it encountered, the turbulence that spun it this way and that, all of these experiences are encoded in its shape. Scientists call snowflakes hieroglyphs from the clouds, because if you know how to read them, they tell you stories about conditions thousands of feet above your head. Tonight, we will follow a snowflake from its very first moment of existence, high in the cold darkness of a winter cloud, down through its long, tumbling descent, until it finally comes to rest on the ground below. We will discover why snowflakes always have 6 sides, why they form such elaborate branching patterns, and why, despite the billions upon billions that fall each winter, no two are ever truly identical. We will meet the scientists who dedicated their lives to understanding these frozen crystals, and we will learn about the physics and chemistry that transform simple water molecules into intricate geometric masterpieces. Let's begin. The birth of a snowflake. From vapor to ice. High above the earth, where the air grows thin and brutally cold, winter clouds stretch across the sky like dark continents suspended in space. Inside these clouds, invisible to our eyes, water exists in a form we rarely think about in our daily lives. It is not liquid. It is not solid. It is water vapor, individual molecules of H2O floating freely through the frigid air, bouncing and tumbling in the constant, invisible motion that defines all gases. The temperature in these clouds can drop to 20, 30, even 40 degrees below 0 Fahrenheit. At such temperatures, you might expect water vapor to freeze instantly into ice. But here is where the physics becomes interesting. Water vapor does not want to freeze easily. Even at these extreme temperatures, the molecules resist forming ice crystals. They remain stubbornly in their gaseous state, supercooled water vapor that exists far below the temperature at which you would expect it to solidify. For a snowflake to begin its existence, something unusual must happen. A nucleation event must occur. This is a term scientists use to describe the moment when a phase change begins, when vapor becomes solid, when liquid becomes gas, when one state of matter transforms into another. For ice to form in a cloud, the water vapor needs something to grab onto, a tiny particle that serves as the seed around which a crystal can begin to grow. These nucleation particles drift through the atmosphere in astonishing variety. Specks of dust lifted from deserts thousands of miles away. Tiny grains of pollen released by plants and carried aloft on winds. Microscopic particles of clay or soot. Salt crystals from ocean spray that evaporated and rose into the high atmosphere. Even certain bacteria that live in clouds. Microorganisms that have evolved the ability to trigger ice formation. All of these serve as the foundation upon which snowflakes build themselves. When conditions align properly, when the temperature drops low enough, and a water vapor molecule happens to collide with one of these particles at just the right moment, something remarkable occurs. The molecule sticks. It freezes onto the particle's surface. And then another molecule arrives and freezes beside it. And another. And another. Molecule by molecule, an ice crystal begins to form. This process is called deposition, and it is fundamentally different from the way ice forms in your freezer. When you make ice cubes, liquid water cools down until it freezes into solid ice. That is called freezing or solidification. But in clouds, there is no liquid water involved in most snowflake formation. The water goes directly from vapor, the gaseous state, to ice, the solid state, without ever passing through the liquid phase. This direct transformation is what defines deposition. The very first ice crystal that forms is impossibly small, far too tiny to see with the naked eye. It might contain only a few hundred or a few thousand water molecules. But it has already taken on a specific shape, a shape that will define everything that comes after. It is a hexagonal prism, a three-dimensional structure with two flat hexagonal faces on the top and bottom, and 6 rectangular faces connecting them around the sides. Why hexagonal? Why not a square or a triangle or some other shape? The answer lies in the molecular structure of water itself, in the way that individual H2O molecules prefer to bond with one another. But we will explore that mystery in depth shortly. For now, know that this initial hexagonal shape is the genetic code, so to speak, of the snowflake. Everything that grows from this tiny seed will reflect and elaborate upon this 6-sided geometry. As the embryonic crystal tumbles through the cloud, more water vapor molecules collide with it and stick. The crystal grows larger, but it does not grow uniformly in all directions. Certain faces of the crystal attract water molecules more readily than others. Certain edges grow faster. The flat, hexagonal faces on the top and bottom might grow outward, making the crystal wider but flatter, like a tiny hexagonal dinner plate. Or the 6 edges of the hexagon might begin to extend outward, forming the beginnings of what will become the 6 arms or branches of a classic snowflake. The crystal is still incredibly small at this point, perhaps a few hundredths of a millimeter across. If you could somehow pluck it from the cloud at this early stage and examine it under a microscope, you would see a simple geometric form, clean lines and flat faces, a miniature piece of precise crystalline architecture. There would be no elaborate branching yet, no intricate dendritic patterns, just the fundamental hexagonal prism growing slowly as it drifts through the supercooled cloud. But the snowflake's journey is only beginning, and the atmosphere through which it will fall is not uniform. Temperature and humidity vary from place to place within the cloud, and they will vary even more dramatically as the crystal begins its long descent toward the earth below. Each change in conditions will alter how the crystal grows. Each new environment it encounters will add new features, new patterns, new complexity to its structure. The snowflake is about to become a traveler through many different worlds, each one leaving its mark on the growing ice. The hexagonal mystery. Why 6 sides? If you have ever really looked at snowflakes, whether in photographs or caught on your sleeve during a snowstorm, you have probably noticed that they almost always display 6-fold symmetry. 6 arms radiating from a central point, 6 corners on a hexagonal plate, 6 branches reaching outward like the spokes of a wheel. This 6-sidedness is so consistent, so fundamental to snowflakes, that it seems to be written into their very nature. And, indeed, it is. The 6-fold symmetry of snowflakes is not an accident or a coincidence. It is a direct consequence of how water molecules bind together when they freeze into ice. To understand this, we need to think small, incredibly small, down to the level of individual atoms and the forces that hold them together. A water molecule is deceptively simple. 1 oxygen atom bonded to 2 hydrogen atoms. H2O. You learned this in school, probably so long ago that it feels like fundamental knowledge, as obvious as the fact that the sky is blue or that stones are hard. But like many simple things, water becomes endlessly complex when you examine it closely. The oxygen atom sits at the center of the molecule, larger and heavier than the 2 hydrogen atoms attached to it. Those hydrogen atoms are not positioned randomly. They bond to the oxygen at a very specific angle, approximately 104.5 degrees apart. If you could see a water molecule, it would look like a wide V shape, with the oxygen at the vertex and the 2 hydrogen atoms at the ends of the 2 arms. This shape, this particular geometry, matters enormously. It creates what chemists call a polar molecule, meaning that one part of the molecule has a slight negative electrical charge, while another part has a slight positive charge. The oxygen side of the molecule is slightly negative. The hydrogen side is slightly positive. These charges are weak, but they are strong enough to make water molecules attract each other in specific ways. When water molecules come together, the positive hydrogen end of one molecule is attracted to the negative oxygen end of another molecule. This attraction is called a hydrogen bond, and while it is much weaker than the bonds holding the atoms within each molecule together, hydrogen bonds are strong enough to profoundly influence how water behaves. In liquid water, these hydrogen bonds form and break constantly. Molecules slide past one another, bonding briefly and then releasing. creating the fluid, flowing nature of water in its liquid state. But when water freezes, when it transforms from liquid to solid ice, the molecules lock into position. The hydrogen bonds become permanent, holding each molecule in a fixed relationship to its neighbors. And here is where the hexagonal pattern emerges. When water molecules arrange themselves into ice, each molecule bonds to 4 others in a very specific geometric pattern. If you could see the arrangement from the right angle, you would notice that the molecules form repeating hexagons, 6 molecules around a central space, and these hexagons stack and connect to form a 3-dimensional crystalline lattice. This hexagonal arrangement is the most stable, most energetically favorable way for water molecules to pack themselves together when they freeze. The angles work out perfectly. The hydrogen bonds align in ways that minimize energy while maximizing stability. The result is ice with a built-in hexagonal structure at the molecular level. When an ice crystal grows, it must follow this internal architecture. Water vapor molecules arriving at the crystal's surface do not attach themselves randomly. They fit into the existing lattice structure, extending it, building upon it, but always following the same hexagonal pattern that is encoded in the way water molecules bond to one another. Imagine building with toy blocks that only connect at certain angles. You could build many different structures, tall towers or flat platforms or branching forms, but all of them would reflect the constraints of how the blocks fit together. Ice crystals are similar. They can grow into many different shapes, as we will see, but all of them are variations on the fundamental hexagonal theme. This is why snowflakes have 6 sides, 6 corners, 6 arms. Not because of some cosmic rule about the number 6, but because of the specific angle at which hydrogen bonds form between water molecules, because of the geometry that emerges when H2O molecules lock together into a crystalline solid. It is beautiful, in a way, how something as grand and visible as a snowflake's 6-fold symmetry emerges from something as small and invisible as the angle between 2 hydrogen atoms bonding to a single oxygen atom. The macroscopic world we can see and touch is shaped, always, by the microscopic world of atoms and molecules following their own simple rules. Scientists have known about the hexagonal structure of ice for about a century now, ever since X-ray crystallography allowed researchers to peer into the atomic structure of crystals. But people noticed the 6-sided nature of snowflakes long before they understood why. Johannes Kepler, the great astronomer and mathematician, wrote about snowflakes in 1611, asking why they always seemed to have 6 corners. He speculated that they might be formed by stacking spheres, comparing them to the 6-fold patterns you see when you stack cannonballs or oranges. He was remarkably insightful, even though he had no way of knowing about atoms or molecules or hydrogen bonds. It would be more than 300 years before science could fully explain what Kepler observed with his own eyes on a winter day in Prague. The 6-sided snowflake is a message from the molecular world, a pattern made visible by the simple act of water freezing in cold air. The journey through the clouds. Once an ice crystal nucleates and begins to grow, it does not remain stationary in the cloud where it formed. The crystal is small and light, easily carried by air currents, but as it grows larger and heavier, it begins a gradual descent. This falling journey can last anywhere from several minutes to over an hour, depending on how high the crystal formed and how much it is buffeted by updrafts within the cloud. And during this journey, the snowflake is constantly growing. Water vapor continues to condense onto its surface, adding molecule after molecule to the expanding structure. But here is what makes each snowflake's journey unique. The conditions the crystal encounters are never quite the same for any two crystals, and those conditions determine exactly how the crystal grows. Temperature and humidity are the two primary factors that control ice crystal growth, and both of these vary continuously within a cloud and between different altitudes in the atmosphere. A cloud is not a uniform mass of cold, moist air. It is a dynamic, turbulent, constantly shifting environment with temperature gradients, pockets of higher and lower humidity, regions of upward rushing air, and regions of calm descent. As a snowflake tumbles through this complex environment, the conditions around it change constantly. It might form in a region of the cloud where the temperature is negative 15 degrees Celsius and the humidity is relatively high. Then, an updraft might carry it to a colder region at negative 20 degrees where the air is drier. Then, it might fall into a slightly warmer zone at negative 10 degrees with much higher humidity. Each of these zones has its own characteristic effect on how the crystal grows. The relationship between temperature, humidity, and crystal shape is summarized in what scientists call a morphology diagram, a kind of map that shows which types of snowflakes form under different atmospheric conditions. We will explore this diagram in detail shortly, but for now, understand that it represents decades of careful observation and experimentation by scientists studying how ice crystals develop. What makes the snowflake's journey so important is that all 6 arms or branches of the crystal experience these changing conditions at the same time. The snowflake is small enough that its entire structure exists within essentially the same local environment at any given moment. When it tumbles into a warmer region, all 6 arms experience that warming simultaneously. When humidity increases, all 6 arms sense that increase together. This shared experience is why snowflakes develop such striking symmetry despite their complexity. The 6 arms are not coordinating with each other. There is no communication between one side of the snowflake and the other, no master plan directing growth. But because all 6 arms are exposed to the same sequence of temperature and humidity changes at the same time, they respond in the same way. They grow in parallel, following the same developmental path, each arm an independent echo of the others. Imagine 6 musicians sitting in a circle, each playing the same piece of music but unable to hear one another. If they are all reading from the same sheet of music and all starting at the same moment, they will play in synchrony not because they are coordinating, but because they are following the same instructions. The 6 arms of a snowflake are similar. They all respond to the same environmental cues, and so they develop in nearly identical ways, creating the snowflake's characteristic symmetry. But nearly identical is not perfectly identical. Upon very close inspection, you will usually find subtle differences between the arms. One might be slightly longer, another might have a branch that splits at a slightly different angle. These tiny asymmetries arise because the snowflake is not completely still as it falls. It tumbles and rotates. Sometimes one corner leads the descent while the others trail behind. Sometimes the crystal tilts or spins. These motions mean that even though all 6 arms are in the same general environment, they might experience microscopically different conditions. Tiny variations in the flow of air past them, or the concentration of water vapor immediately around them. The atmosphere is a turbulent place. Imagine falling through a cloud, spinning slowly as you descend. Sometimes you are oriented vertically, sometimes horizontally. Sometimes you pass through a small region where water vapor is slightly more concentrated. Sometimes you drift through a momentary eddy in the air. All of these microscopic variations affect how and where water molecules attach to the growing crystal. The result is that snowflake symmetry is always approximate, always beautiful, but never absolutely perfect. The 6 arms will look strikingly similar when you first glance at them. Similar enough that the snowflake appears to have 6-fold radial symmetry. But if you examine each arm carefully, you will find the small imperfections that tell the story of the snowflake's turbulent journey through the sky. And each snowflake takes a different journey. Even 2 crystals that form right next to each other in the same cloud will be caught by different air currents. One might rise higher in an updraft before beginning its final descent. Another might fall through a slightly different path, passing through subtly different temperature and humidity zones. The number of possible paths through a cloud is essentially infinite, and each path produces a different sequence of growth conditions. This is the heart of why no 2 snowflakes are alike. It is not just that they are complex. It is that their complexity is the accumulated result of a journey that is unique to each crystal. A path through an endlessly variable atmospheric environment that will never be repeated in quite the same way. The morphology diagram, a map of possibilities. If you want to understand the astonishing diversity of snowflake shapes, you need to understand the morphology diagram. This is one of the most important scientific tools for studying snow crystals, and it represents the work of many researchers over many decades, all trying to answer a simple question: what determines the shape of a snowflake? The story of the morphology diagram begins in the 1930s in Japan, with a physicist named Ukichiro Nakaya. Nakaya was fascinated by snowflakes, and he wanted to study them scientifically, not just by collecting natural snowflakes as they fell, but by growing ice crystals under controlled laboratory conditions, where he could vary the temperature and humidity precisely and observe how the crystals responded. His experimental setup was ingenious for its time. He would suspend a rabbit hair or a fine thread inside a refrigerated chamber, then introduce water vapor and wait for ice crystals to nucleate and grow. By adjusting the temperature and humidity inside the chamber, he could create different atmospheric conditions and observe what kinds of crystals formed under each set of conditions. What Nakaya discovered was remarkable. He found that the shape of an ice crystal depends strongly on both temperature and humidity, and that these 2 factors combine to produce a surprising variety of distinct crystal forms. Some conditions produced flat hexagonal plates. Others produced long columnar prisms. Still others produced an elaborate branching dendrites with intricate patterns. and the boundaries between these different regimes were sharp and reproducible. Nakaya compiled his observations into a diagram showing which crystal shapes appeared at which combinations of temperature and humidity. This diagram, published in the 1940s, was the first comprehensive map of ice crystal morphology, and it revolutionized the scientific understanding of snowflakes. Later, scientists have refined and extended Nakaya's original work. Most notably, Kenneth Liebrecht, a physicist at the California Institute of Technology, who has dedicated much of his career to understanding ice crystal growth. Liebrecht has grown thousands of snow crystals in laboratory chambers, photographed them extensively, and pushed the morphology diagram to more extreme conditions, including temperatures as low as -70 degrees Celsius. The modern morphology diagram is organized with temperature along one axis and supersaturation, a measure of humidity above 100% along the other axis. Different regions of the diagram correspond to different crystal shapes. Near 0 degrees Celsius, just below freezing, crystals grow as thin, flat plates. As the temperature drops to around -3 or -4 degrees, the plates become thicker. Then, around -5 degrees Celsius, something fascinating happens. The growth switches from plates to columns. Long, thin columnar prisms form, sometimes looking like hexagonal pencils or needles. Drop the temperature further, and around -10 to -15 degrees, the crystals switch back to plate-like growth, but now they form larger, more elaborate plates. This is the temperature range where classic stellar dendrites develop, those beautiful branching snowflakes that look like six-pointed stars with intricate, feathery arms. These are the snowflakes you see on holiday cards and decorations, the iconic winter crystal. Below -20 degrees, the pattern switches yet again, this time to a regime where both plates and columns can form depending on the exact conditions. And at even colder temperatures approaching -40 degrees, the crystals become simpler again, forming small, compact shapes. Humidity plays a role as well. At low supersaturation levels, crystals tend to be simple and geometric, with clean faceted surfaces. As humidity increases, the crystals become more elaborate and complex. The highest humidity levels produce the most intricate forms. Extremely long, thin needles around -5 degrees, and large, elaborate, stellar dendrites around -15 degrees. What makes the morphology diagram so useful is that it allows scientists to infer atmospheric conditions from the shape of fallen snow crystals. If you go outside during a snowstorm and examine the crystals landing on your coat, you can make educated guesses about what is happening thousands of feet above your head. Are they thin plates? The temperature up there is probably around -2 degrees. Are they long needles? You are likely seeing crystals that formed around -5 degrees. Stellar dendrites, the sweet spot around -15 degrees. Nakaya famously said that snowflakes are like hieroglyphs from the clouds. By learning to read the shapes, you can decode messages about the invisible atmospheric conditions that created them. But here is something truly mysterious. Despite all the research, despite all the careful observations and laboratory experiments, no one fully understands why the morphology diagram looks the way it does. Why does ice switch from plate-like growth to columnar growth and back to plates as temperature decreases? What is happening at the molecular level to cause these dramatic shifts in crystal habit? Scientists can describe the phenomenon. They can measure it. They can reproduce it reliably in laboratory chambers. But they cannot yet explain it from first principles. They cannot start with the fundamental physics of how water molecules attach to ice surfaces and derive the morphology diagram. The theoretical understanding is incomplete. This is one of the wonderful things about science, how even something as commonplace as a snowflake can harbor deep mysteries. The morphology diagram is like a map to a country we can visit but do not yet fully understand. We know the landscape. We have charted the territories, but we are still working to comprehend the rules that created this landscape in the first place. Kenneth Liebrecht has spent years trying to crack this mystery, growing crystals under precisely controlled conditions and studying the fine details of how they develop. He has made progress, uncovering some of the mechanisms involved, but the complete picture remains elusive. It is a reminder that nature always holds surprises, always has depths that require patience and careful observation to explore. The mathematics of uniqueness. There is an old saying that no two snowflakes are exactly alike. You have probably heard it. Perhaps you have even said it yourself. But is it really true? How can we possibly know that among the countless billions upon billions of snowflakes that have fallen throughout Earth's history, no two have ever been identical? The answer lies in mathematics, specifically in probability and combinatorics, the branch of mathematics that deals with counting possibilities and combinations. A typical snowflake, a decent-sized stellar dendrite of the kind you might catch on your mitten, contains approximately 1 quintillion water molecules. A quintillion is a 1 followed by 18 zeros. Written out, it looks like this. 1. That is a number so large it is difficult to comprehend intuitively. To put it in perspective, if you tried to count to 1 quintillion, counting one number per second without ever stopping, it would take you more than 30 billion years. The universe itself is only about 14 billion years old. The number of water molecules in a single snowflake exceeds, by several orders of magnitude, the number of seconds that have passed since the Big Bang. Now, consider that each of these molecules must be placed in a specific location within the crystal's structure. As the snowflake grows, each arriving water molecule has choices about exactly where it will attach to the existing lattice. There are preferred attachment sites, places where the crystal is actively growing, but even within those sites, there is variability. A molecule might attach at one edge or another. It might fill in a corner or extend an existing face. Quantum mechanical effects, thermal vibrations, the exact angle of approach, all of these factors influence precisely where each molecule ends up. The number of possible ways to arrange 1 quintillion water molecules into a snowflake structure is incomprehensibly vast. It is so large that mathematicians would write it using exponential notation, probably something like 10 to the power of many thousands. The number of possible snowflake configurations dwarfs the number of atoms in the observable universe. Now, add in the fact that as the snowflake grows and falls through the atmosphere, it experiences a constantly changing environment. Every fraction of a second, the the temperature might shift by a tiny amount. The humidity might fluctuate. An air current might spin the crystal or carry it into a region with slightly different conditions. Each of these environmental variations affects how the crystal grows in that moment, which in turn affects how it will grow in the next moment. Kenneth Liebrecht, the physicist we met earlier, compares this to shuffling a deck of cards. There are about 67 possible ways to arrange a standard deck of 52 cards. That is 8 followed by 67 zeros, a stupendously large number. If you shuffled a deck once per second from the beginning of the universe until now, the odds that you would ever get the same arrangement twice are essentially zero. The number of possible arrangements is so vast compared to the number of shuffles that repetition is not impossible in a strict mathematical sense, but it is so unlikely as to be effectively impossible in practice. Snowflakes are like that, except with far more complexity. Each snowflake is shaped by the accumulated effect of countless tiny events during its formation and growth, each one adding another layer of detail, another branch of the possibility tree. The odds of two snowflakes following exactly the same growth history, molecule by molecule, are so vanishingly small that we can confidently say it has never happened naturally. But there is an interesting caveat to this. In laboratory settings, where scientists can control temperature and humidity very precisely and grow crystals under nearly identical conditions, it is possible to create snowflakes that look virtually identical when examined at normal magnifications. These twin snowflakes form in such carefully controlled environments that they follow very similar growth paths and develop very similar macroscopic structures. In 1988, a scientist named Nancy Knight reported finding what appeared to be two nearly identical snowflakes in a natural snowfall. But when these crystals were examined closely, differences appeared. At high magnification, the supposedly identical twins showed variations in the fine details of their structure. The overall branching pattern was similar, but the microscopic placement of molecules differed. So the statement, "No two snowflakes are exactly alike," remains true in the sense that matters. No two natural snowflakes, formed in the chaotic, variable environment of real clouds and real winter storms, have ever been found to be identical at the molecular level. And, given the mathematics involved, it is extraordinarily unlikely that any two ever will be. This uniqueness is not a fundamental law of physics. It is simply a consequence of how incredibly many ways there are to build a snowflake, and how incredibly variable the conditions are under which snowflakes form. Each snowflake is the product of its own unique history, and that history is written into its structure in ways that can never be perfectly replicated. When you catch a snowflake on your hand and look at it in those few seconds before your body heat melts it away, you are looking at something that has never existed before and will never exist again. You are witnessing a unique creation, a singular expression of physics and chemistry and chance. There is something profound in that thought, something that makes the simple act of watching snowfall feel a little bit like witnessing miracles. Symmetry and asymmetry, the 6 arms. One of the most striking features of snowflakes is their symmetry. Look at a well-formed stellar dendrite, one of those classic 6-armed snowflakes, and you will see 6 branches radiating from a central hexagon, each branch remarkably similar to the others. The overall pattern appears almost deliberate, as though someone designed the snowflake with a ruler and compass to ensure perfect six-fold symmetry. But, as we discussed earlier, this symmetry arises not from coordination between the arms, but from the fact that all 6 arms experience the same growth conditions at the same time. They are like 6 separate snowflakes growing independently, but following the same environmental instructions. Yet, when you examine snowflakes very carefully, either in person with a magnifying glass or in photographs taken with specialized microscopes, you discover that the symmetry is never quite perfect. One arm might be slightly longer than the others. A branch that appears on 5 of the arms might be missing or differently shaped on the 6th. Small bumps and ridges that should mirror each other across the snowflake's center often show subtle variations. These asymmetries tell us something important about how snowflakes grow and about the environment through which they fall. Remember that the atmosphere is turbulent. Air does not flow smoothly and uniformly. It eddies and swirls. Pockets of slightly different humidity appear and disappear. Microscopic variations in temperature form and dissolve. As a snowflake tumbles through this environment, it does not remain in a fixed orientation. It spins. It tilts. Sometimes it falls edge first, sometimes flat. As it rotates, different arms temporarily lead the descent, meaning they encounter the incoming flow of air first. This can create momentary differences in the rate at which water vapor reaches different parts of the snowflake, leading to temporary differences in growth rate. Additionally, the very act of growing can create instabilities. This is where the physics becomes subtle and fascinating. When an ice crystal grows from water vapor, the process releases heat. Ice is warmer than the vapor from which it forms, just as water is warmer than the steam from which it condenses. This latent heat must flow away from the growing crystal into the surrounding air. At the sharp tips of a growing branch, heat has difficulty escaping efficiently. The tip is like a tiny hot spot, slightly warmer than the air around it, and this warmth can affect how water molecules attach. Sometimes this leads to what the scientists call branching instability, where the growing tip becomes unstable and sprouts side branches. We will explore this in more detail when we discuss dendritic snowflakes. But for now, understand that these growth instabilities can introduce small random variations into the structure, adding to the asymmetry. The remarkable thing is not that snowflake arms differ slightly from each other. The remarkable thing is that they are so similar despite all the sources of variation. This similarity, this approximate symmetry, arises because the 6 arms are physically close together, all part of the same small crystal, and so they share most of their environment most of the time. The differences accumulate slowly, introducing only subtle asymmetries rather than wildly different growth patterns. Imagine 6 trees planted in a circle, very close together in a single garden plot. Over time, they will grow in broadly similar ways because they share the same soil, the same sunlight, the same rainfall. But they will not be identical. One might grow slightly taller if it happens to catch a bit more sun. Another might develop a branch at a certain height where the others do not if a bird happened to land there and damage a growing shoot. The trees share an environment, but each has its own micro-history of tiny events that influence its development. Snowflakes are similar. The 6 arms share a journey, but each arm has its own micro-history of growth events. The result is structures that balance symmetry and individuality, pattern and variation, order and chaos. There is something almost philosophical about this. The snowflake seems to embody a principle that appears throughout nature, that pattern and variation coexist, that order emerges not from rigid control but from shared responses to shared environments, and that perfect symmetry is less interesting and less beautiful than the approximate living symmetry found in real natural forms. The gallery of forms. When most people picture a snowflake, they imagine a stellar dendrite, a flat plate with 6 elaborate feathery arms extending outward from a central hexagon, each arm branching and rebranching into increasingly fine structures. The whole crystal looking like a tiny frozen fern or a 6-pointed star made of ice lace. Stellar dendrites are indeed beautiful, and they are certainly one of the most photogenic types of snow crystals. They are the snowflakes that appear on greeting cards, in decorations, as symbols of winter. But they represent only one form among many that snow crystals can take. The diversity of snowflake shapes is far greater than most people realize. There are simple hexagonal plates, thick and flat like tiny tiles. There are sectored plates, where the hexagon is divided into 6 wedge-shaped regions with distinct markings. There are stellar plates, simpler and smaller than stellar dendrites, with 6 broad arms but without the elaborate branching. There are columns, long prismatic shapes like miniature hexagonal pencils. There are needles, extremely thin columnar crystals that can grow to surprising lengths. There are capped columns, where a crystal grows first as a column, then develops thin hexagonal plates on both ends. There are hollow columns, columnar crystals with a hollow core running down their length. There are bullet rosettes, where several columnar crystals grow joined together at one end. There are double plates, where 2 hexagonal plates form at different points along a short column. There are split plates and split stars, where the arms split and fork in unusual ways. And beyond all these distinct types, there are irregulars, snowflakes that do not fit neatly into any category. They might be fragments broken from larger crystals during collision. They might be crystals that formed under rapidly changing conditions and developed multiple conflicting growth patterns. They might be clusters of small crystals that stuck together, or crystals coated with frost, or any of 100 other variations. In fact, irregulars are by far the most common type of snowflake. When you look at falling snow, most of what you see consists of small, irregular ice particles. The beautiful, symmetric stellar dendrites are actually relatively rare, forming only under specific atmospheric conditions that do not occur in every snowstorm. Kenneth Librecht, whose work we keep returning to because he is one of the leading experts on snow crystals, has developed a classification system that includes 35 main types of snow crystals and numerous subtypes. This classification is somewhat arbitrary in the same way that classifying types of breed or breeds of dogs is arbitrary. Nature produces a continuum of forms, and humans impose categories to help organize and discuss them. But the categories are useful. They give us a vocabulary for talking about the shapes we observe. Let us explore a few of the more common and interesting types in a bit more detail. Stellar dendrites, those classic branching snowflakes, form at temperatures around -15 degrees Celsius under conditions of relatively high humidity. The term dendrite comes from the Greek word for tree, and it refers to the branching, tree-like pattern of growth. These crystals start as simple hexagonal plates, but as they grow, instabilities develop at the 6 corners. The corners begin to extend outward, forming the beginnings of arms. As each arm grows longer, reaching out into the surrounding air to gather more water vapor. The very tip of the arm experiences the highest concentration of vapor. This makes the tip grow faster than the rest of the arm, creating a kind of positive feedback where the fastest growing parts continue to grow even faster. But the tip also becomes unstable. Small, random variations in the shape of the tip get amplified, and side branches begin to sprout. These side branches then develop their own instabilities and sprout smaller branches, creating the fern-like, fractal-like patterns that make stellar dendrites so visually compelling. Sectored plates are flat hexagonal crystals, where the surface shows a distinct pattern dividing the crystal into 6 sectors, like cutting a hexagonal pie into 6 equal slices. These markings reflect internal structures in the ice crystal, regions where the molecular lattice has slightly different orientations, or where growth has proceeded in slightly different ways. They form at temperatures just below freezing, around -2 or -3 degrees Celsius. Columns form around -5 degrees Celsius. At this temperature, for reasons that scientists still do not fully understand, the crystal grows faster along its vertical axis than horizontally. Instead of a flat plate, you get a long columnar prism. These columns are often small and simple, but they can be quite beautiful under magnification, showing clean, faceted faces and sometimes hollow cores. Needles are an extreme version of columnar growth. At very high humidity levels around -5 degrees, the columns become extremely elongated, forming thin ice needles that can be surprisingly long relative to their diameter. A bundle of these needles falling together can look almost like tiny icy splinters drifting through the air. Capped columns are especially interesting because they tell a story of changing conditions during growth. These crystals start as columns, forming around -5 degrees. Then, as they fall, or as conditions in the cloud change, they move into a temperature regime around -15 degrees where plate-like growth dominates. Thin, hexagonal plates begin to grow on the 2 ends of the column like little caps. Sometimes these caps develop branches of their own, creating elaborate structures that combine both columnar and plate-like features. Rimed crystals deserve special mention as well. Rime is not a growth form like plates or columns. It is a surface feature that occurs when supercooled water droplets in the cloud collide with a falling snow crystal and freeze onto it instantly. This coats the crystal in a layer of frost, obscuring its original shape and giving it a bumpy, frosted appearance. Heavily rimed crystals can become so coated that they transform into graupel, small, soft pellets of rime-covered snow that look almost like tiny white peas. Each of these crystal types reflects a different combination of temperature, humidity, and growth history. A trained observer can look at a collection of fallen snow and infer quite a bit about the atmospheric conditions through which the snow fell. Mostly stellar dendrites? The temperature in the cloud was probably around -15 degrees. Mix of plates and columns? The snow likely formed in a layered cloud with different temperature zones. Lots of irregular broken fragments? The snow crystals were tumbling through turbulent air where they collided with each other frequently. The diversity of snowflake forms is a testament to how sensitive crystal growth is to its environment, and to how variable that environment can be. It is also a reminder that when we talk about snowflakes in the abstract, we are really talking about a whole family of related structures, each one shaped by its own particular history. Wilson Bentley, the snowflake pioneer. Before we can fully appreciate the modern scientific understanding of snowflakes, we should pause to honor a man who dedicated his life to studying these crystals at a time when most people thought of them as nothing more than frozen water. His name was Wilson Alwyn Bentley, though he is better known by his nickname, Snowflake Bentley. Bentley was born in 1865 in Jericho, Vermont, a small farming community where winter arrived early and stayed late, where snow was a constant presence for months each year. As a child, he became fascinated by snowflakes. His mother, who had been a school teacher, gave him an old microscope, and Bentley spent hours examining snowflakes under its lens, marveling at the intricate patterns he found. He tried to draw what he saw, sketching snowflakes as accurately as he could before they melted. But the crystals melted too quickly, and his drawings, no matter how careful, could not capture all the detail he observed. He became obsessed with the idea of photographing snowflakes, of creating permanent records that would preserve their beauty and allow for careful study. In 1885, at the age of 20, Bentley successfully attached a camera to a microscope and took his first photograph of a snowflake. The process was painstaking. He had to work in unheated sheds to keep the snowflakes from melting. He had to catch individual crystals on black velvet, quickly transfer them to glass slides, position them under the microscope, focus carefully, and expose the photographic plate, all before the crystal melted or sublimated away. But Bentley persisted. Over the following decades, he photographed more than 5,000 snowflakes, creating the first comprehensive photographic record of snow crystal diversity. His photographs revealed to the world just how varied and intricate snowflakes could be. Before Bentley, most people had never really seen a snowflake up close. After his work became known, it was impossible to look at snow the same way again. Bentley did not just take photographs. He studied his images carefully. He noticed patterns. He observed that certain shapes appeared more commonly under certain weather conditions. He noted the six-fold symmetry and began to wonder why it was so consistent. His work was, in many ways, the beginning of modern snowflake science. He also wrote about snowflakes with a sense of wonder and poetry. "Every crystal was a masterpiece of design," he once wrote, "and no one design was ever repeated. When a snowflake melted, that design was forever lost. Just that much beauty was gone, without leaving any record behind." Bentley's neighbors in Vermont thought he was eccentric, spending so much time and effort photographing snow. Farming was hard work, and here was Wilson out in the cold, bent over his equipment, capturing images of something that would melt away to nothing in minutes. But Bentley did not care what others thought. He had found something that fascinated him utterly, and he pursued that fascination with single-minded dedication. In 1931, Bentley walked 6 miles through a blizzard to photograph snowflakes. He developed pneumonia and died a few days later at the age of 66. He had spent most of his life on that farm in Vermont, never traveled far, never sought fame or fortune. He simply loved snowflakes, and he wanted to share that love with anyone who would look at his photographs. Before his death, Bentley donated a large portion of his photographic collection to the Smithsonian Institution, ensuring that his work would be preserved against all possibility of loss and destruction through fire or accident, as he wrote in his letter to the Smithsonian. Today, Bentley's photographs are recognized as both scientific treasures and works of art. They appear in books, in museums, in online galleries. They have inspired scientists, photographers, artists, and countless people who simply find beauty in the natural world. And they remind us that sometimes the most important scientific work is done not in large institutions with expensive equipment, but by dedicated individuals who see something wonderful in the everyday world around them and refuse to let that wonder go unrecorded. Bentley was not a trained scientist. He had no formal education beyond basic schooling. He was a farmer who loved snowflakes. But his contribution to science was immense. He showed that careful observation, patience, and passion could reveal truths about nature that had been hidden in plain sight, falling from the winter sky by the billions, but never really seen until one man decided to look closely. Modern mysteries, what we still don't know. You might think that after more than a century of scientific study, after thousands of photographs, after laboratory experiments and computer simulations and detailed observations, we would understand everything about how snowflakes form and why they take the shapes they do. But you would be wrong. Snowflakes still harbor mysteries. Despite all the progress that has been made, there are fundamental questions that remain unanswered, aspects of ice crystal growth that continue to puzzle scientists. The biggest unsolved mystery is the morphology diagram itself. Why does ice crystal growth switch from plates to columns and back to plates as temperature changes? What is happening at the molecular level when the temperature crosses from -4 degrees to -5 degrees that causes such a dramatic shift in crystal behavior? Scientists can measure this phenomenon precisely. They can reproduce it reliably in laboratory chambers. They can show you exactly what temperature and humidity combinations produce which crystal shapes. But they cannot explain it from first principles. They cannot start with the fundamental physics of water molecules and derive why the morphology diagram looks the way it does. Kenneth Librecht, who has spent years working on this problem, describes it as one of the most frustrating mysteries in his career. He has made progress. He has identified some of the mechanisms involved, particularly related to how water molecules attach to different faces of the ice crystal, and how heat and vapor diffuse around a growing crystal. But the complete picture eludes him. Part of the difficulty is that ice crystal growth involves multiple physical processes operating simultaneously and interacting with each other in complex ways. There is diffusion of water vapor through the air toward the crystal. There is diffusion of heat away from the crystal as molecules freeze and release latent heat. There is the attachment kinetics of individual water molecules sticking to the ice surface. There are surface effects, where the atomic structure of the crystal face influences how readily molecules attach. There are instabilities that cause smooth surfaces to become rough or flat plates to sprout branches. All of these processes are reasonably well understood individually, but the way they combine and influence each other during crystal growth creates emergent behaviors that are difficult to predict or explain. The morphology diagram is one of those emergent phenomena, a pattern that arises from the interaction of many simpler processes but is not easily reduced to those processes. This is common in science. The fundamental laws are often simple. Newton's laws of motion are simple. The equations of fluid dynamics are well known. But when you apply these simple laws to complex systems, predicting what will happen becomes extraordinarily difficult. Weather forecasting is difficult, not because we do not understand physics, but because the atmosphere is so complex that tracking all the interactions becomes computationally overwhelming. Ice crystal growth is similar. We understand the basic physics, but tracking how that physics plays out in the intricate dance of a growing snowflake remains challenging. Another mystery involves the detailed structure of snow crystal surfaces. Recent research using advanced microscopy techniques has shown that snow crystal surfaces are not smooth and perfect at the molecular level. They have defects, irregularities, steps, and kinks where the atomic lattice is not perfectly ordered. These surface features influence how water molecules attach and where new growth occurs. Understanding these surface structures and their dynamics is essential for fully explaining crystal growth, but observing them is technically challenging. The crystals are delicate. They exist only under very specific conditions. Examining them with high-resolution microscopes without altering them is difficult. There are also mysteries related to how quickly snowflakes grow and how the growth rate depends on conditions. Why do certain types of crystals grow much faster than others under the same conditions? Why does the growth rate show such sharp transitions at certain temperatures? These questions have practical implications too, for weather forecasting and climate modeling, where understanding how quickly ice forms in clouds affects predictions of precipitation and cloud behavior. And then there are the more exotic questions. Why do some snowflakes occasionally show triangular symmetry instead of hexagonal? What causes the rare 12-branched snowflakes that have been observed? Why do certain growth conditions produce split arms or unusual scrolling patterns? Each of these questions represents an opportunity for future research, a puzzle waiting to be solved. And solving them will require not just more observations or more experiments, but deeper theoretical understanding of how crystal growth works at the molecular level. There is something encouraging about these unsolved mysteries. They remind us that science is not a closed book, that even familiar phenomena can hold surprises, and that there is always more to learn. A snowflake is made of nothing but water, one of the most common substances on Earth. And yet we still do not fully understand how it grows. That is humbling, and it is also exciting. Growing snowflakes in the laboratory. One of the reasons our understanding of snowflakes has advanced so much in recent decades is that scientists have learned to grow snow crystals in laboratory chambers where they can control the conditions precisely and observe the growth process in detail. The experimental setup is conceptually simple, though the engineering details can be quite complex. You need a chamber that can be cooled to very low temperatures, typically using liquid nitrogen or specialized refrigeration equipment. You need a way to introduce and control water vapor inside the chamber. You need high-quality optics to observe and photograph the growing crystals. And you need a substrate or suspension method that allows the crystals to grow without being disturbed. In his laboratory at Caltech, Kenneth Liebrecht uses chambers about the size of a large pot, insulated and connected to cooling systems that can maintain steady temperatures from just below freezing down to -40 degrees Celsius or colder. Inside the chamber, water vapor is introduced by evaporating water from a small reservoir. The humidity level can be adjusted by controlling the temperature of this reservoir relative to the temperature where the crystals will grow. Crystals can be grown suspended on thin glass fibers or on specially prepared surfaces. Some researchers grow crystals in free fall, allowing them to drift slowly within the chamber as they develop, which more closely mimics how natural snowflakes form. Others grow crystals fixed in place, which makes it easier to photograph them continuously as they evolve. By carefully setting the temperature and humidity and then letting crystals grow, researchers can test how different conditions affect crystal shape. They can grow plates at -2 degrees, then chill the chamber to -5 degrees and watch the same crystal switch to columnar growth. They can ramp the humidity up and down and observe how the crystal responds, developing more elaborate structures at high humidity and simpler, more compact forms at low humidity. These laboratory experiments have confirmed and refined the morphology diagram that Nakaya first sketched out in the 1930s. They have also revealed many fine details about how crystals develop. For instance, researchers have observed how the tips of growing dendritic arms become unstable and sprout side branches, how these side branches themselves become unstable, how the whole structure develops in a cascading hierarchy of branching growth. The photographs that come out of these laboratories are spectacular. Crystals grown under controlled conditions can be extraordinarily symmetrical and beautiful, sometimes more perfect than any natural snowflake because they grow in a stable, unchanging environment. Liebrecht has produced images of laboratory-grown snowflakes that look almost too perfect to be real, like tiny glass sculptures or computer-generated designs. But the photographs are not just for aesthetic enjoyment. They are scientific data. By comparing images of crystals grown under slightly different conditions, researchers can tease apart the effects of temperature versus humidity, growth rate versus crystal size, and other variables. By analyzing time-lapse sequences showing crystals developing from tiny prisms into elaborate dendrites, they can observe exactly when and how branching begins, how fast different parts of the crystal grow, how the shape evolves over time. Computer modeling has also advanced tremendously. Scientists can now write software that simulates ice crystal growth, incorporating the physics of diffusion, heat transfer, and surface attachment kinetics. These simulations can reproduce many of the features seen in real snowflakes, including the formation of dendritic arms, the development of sectored plates, the transition between different growth modes. A team led by Harold Garke at the University of Regensburg in Germany recently achieved a breakthrough in computational modeling. They created simulations based on fundamental conservation laws and thermodynamics that successfully reproduced both the faceted flat surfaces and the branching dendritic structures seen in real snow crystals. Previous models could produce one or the other, but not both. Garke's work represents a significant step toward a complete physical model of snowflake formation. These simulations revealed some unexpected findings. For instance, they showed that the bonds between surface molecules on the ice crystal have a surprisingly strong influence on growth patterns. They also showed that the speed at which dendritic tips grow is directly proportional to the amount of water vapor in the air. A relationship that had been suspected but not rigorously proven. Laboratory research and computer modeling feed each other. Experiments provide data that modelers need to calibrate and test their simulations. Models provide predictions that experimentalists can test. This back-and-forth process gradually builds up a more complete understanding of the phenomenon. But even with all these tools, fully simulating a snowflake from start to finish remains beyond current capabilities. A complete simulation would need to track an enormous number of water molecules, account for all the complex interactions at the crystal surface, and handle the feedback between growth, heat release, and vapor diffusion. The computational demands are formidable. Still, progress continues. Each year brings new observations, new models, new insights. The snowflake is giving up its secrets slowly, revealing layer by layer the intricate physics that governs its formation. Closing reflection. And so we come to the end of our journey through the science of snowflakes, through the physics and chemistry and history of these tiny frozen crystals that fall from winter skies. We have followed a snowflake from its first moment of existence, nucleating around a speck of dust in a cold cloud, through its long tumbling descent through varying temperature and humidity zones, until it finally comes to rest on the ground, one crystal among countless billions. We have learned why snowflakes have 6 sides, how the angle at which hydrogen bonds form between water molecules creates a hexagonal lattice that defines the crystal's structure. We have seen how temperature and humidity combine to produce an astonishing variety of forms, from simple hexagonal plates to elaborate stellar dendrites with intricate branching arms. We have explored the mathematics that explains why no 2 snowflakes are truly alike, why each one carries within its structure a unique record of the atmospheric journey it took. We met Wilson Bentley, the farmer from Vermont who spent his life photographing snowflakes, who showed the world just how beautiful and varied these crystals could be. We learned about modern scientists like Kenneth Liebrecht, who grow snowflakes in laboratory chambers and work to unravel the remaining mysteries of ice crystal growth. And we discovered that despite more than a century of study, snowflakes still harbor secrets. We still do not fully understand why the morphology diagram looks the way it does. We still cannot predict from first principles exactly what shape a snowflake will take under given conditions. Science has illuminated much, but mysteries remain, waiting for future researchers to solve. There is something wonderful in that. Something reassuring about the fact that nature still surprises us. That even something as familiar as snow can be endlessly complex and fascinating when examined closely. The next time snow falls, I encourage you to go outside if you can and catch a few flakes. Look at them closely before they melt. Notice their six-fold symmetry. Observe the variations, the way each one is a little bit different from the others. And remember that you are looking at structures shaped by forces operating at the molecular level, by temperatures and humidities that varied as the crystal fell, by a journey through the atmosphere that will never be repeated. Each snowflake is a message from the sky, a small frozen artifact of the conditions that created it. And each one is unique, a singular expression of water and cold and chance, existing for a brief moment before melting away and returning to the great cycle of water that moves endlessly between Earth and atmosphere and ocean. If you enjoyed this exploration, please take a moment to like this video and subscribe to the channel. Share your thoughts in the comments. Tell me what you found most interesting, or share your own experiences watching snow, catching snowflakes, wondering at winter's frozen geometry. Your support helps the Sleepy Science Society continue making these gentle journeys through the world of science, one quiet topic at a time. For now, let your mind settle. Let the images of snowflakes drift through your thoughts like snow through air. Imagine the cold touch of winter, the soft sound of falling flakes, the way the world transforms under a blanket of white. Let yourself feel calm, peaceful, ready for rest. The snowflakes have finished their journey, and so, for tonight, have we. Good night, and sleep well.